Good morning, students. This is topic 15, Video A, the rate law. Chemistry is the study of chemical processes. In our study of thermodynamics, we learned that reactions go to equilibrium and there is no potential for them to go any further without work. But now, we want to ask how fast a spontaneous reaction will occur. We recognize that if a reaction is not spontaneous, it can't go. But if it is spontaneous, how fast will it go? Kinetics is the study of the speed of chemical reactions. First, we will need to define what speed means in chemistry, what is called the reaction rate, or rate of reaction. Then we will look at how we can measure reaction rates and how we change reaction rates. To understand how to change rates, we need to understand what rates are dependent upon. And finally, we will look at kinetic theories that help us either explain why reactions behave the way they do, or provide us with a mechanism to change the way a reaction behaves. You might be wondering why we care about kinetics. Kinetics helps us understand how a reaction occurs. Remember that thermodynamics is only about the beginning and the end state. Kinetics, however, is about everything in between, and if we understand that, we can possibly control or create new chemical reactions. We begin our study of kinetics by constructing a model of how reactions occur. Collision theory states that a reaction occurs because of collisions between particles. But the collision has to occur in just the right orientation, with just the right speed or energy. Molecules are colliding all the time, but if they collide with the wrong speed, then the molecules just collide and then move away from one another. Molecules need some energy to rearrange their bonds, and they get this energy from their speed. If the speed is too low, no reaction occurs. Alternatively, molecules can collide with enough speed, but if the orientation is wrong, the reaction cannot occur. For a reaction to occur, molecules must collide with the right orientation, here modeled as sideways, and with enough energy, that is enough speed, to rearrange the bonding. We have to begin thinking about chemical reactions a little differently. Instead of just considering reactants or products, we need to visualize the conversion of reactants to products over time. We can think of an initial time, that is the time when we start the reaction, and then follow the reaction progress. As the reaction proceeds, molecule by molecule, either quickly or slowly, every 2 red dots that become product are converted into 2 blue dots and 1 green dot. Kinetics can be thought of as the time it takes to convert the reactants into products. We can follow the kinetics of a reaction by following the change in the concentration of one of the species, say a reactant species, as time proceeds. We would then graph the concentration on the y-axis and time on the x-axis. As time proceeds, the reactant concentration decreases. Notice that the decrease is not linear. The NO concentration, however, increases as time goes on. Oxygen is also a product, and so its concentration also increases. Notice that the curve for the oxygen reaches its maximum at half the concentration of the curve for NO. This is based on the mole ratio of 2 to 1. So in general, the concentration of reactants decreases with time, and the concentration of products increases with time. We can then use these graphs of concentration versus time to define chemical rates of reaction. The rate of the reaction is how fast the concentration goes up or down as a function of time. The rate of the reaction is not how long it takes for the reaction to occur. The rate is like a speed. When we travel from New York to Pittsburgh, for example, we travel with different speeds, and our speeds might change during the trip. Similarly, the rate of a reaction can occur with different speeds, and the speeds can change over the course of the reaction. We define the rate of a reaction as the change in concentration per change in time. It is conventional to think of rate as a positive quantity. So when we talk about the rate of change of the reactant, in this case NO2, we define the rate as the negative change in concentration over the change in time. Remember that the reactant concentration goes down, and so delta NO2 is a negative number. The rate is then positive, a negative times a negative. The negative sign in the rate expression indicates the disappearance of reactants and makes the rate of change of the reactant a positive number. For the rate of change of a product, we define the rate as the positive change in concentration over the change in time. This is because the product concentration increases with time. If we have two products, like we have here, we have two different rates, one for NO and one for O2, but both rates are positive. As reactions proceed, their rate of reaction changes, but we can think of the rate at any specific point in the reaction. To compute a rate, we draw a tangent line to a point on the curve. The slope of that tangent line is then the rate of the reaction. Slopes of tangent lines are expressed as rise over run, or change in concentration divided by change in time. So the rate is the slope of the line tangent to a particular point on the curve. This will be different for different points on the curve, and we will come back to this idea later. We see then that as the concentration of a reactant or product changes, the rate of the reaction also changes. The rate of a reaction is often, but not always, proportional to the concentration of the reactants raised to some power. So we can write the expression for rate, delta concentration over delta time, as equal to K, the rate constant, times the reactant concentration raised to the nth power. This expression is called the rate law. K is called the rate constant, and the exponent is called the order of the reaction. Determining K and N tell us the rate law. In general, for an arbitrary chemical equation, we can write the rate law as rate equals K times each concentration of reactant raised to a power. The power, in this case M, N, and P, represent the reaction order. The power is usually an integer. It is important to state here that the powers are not given by the stoichiometric coefficients. Sometimes the powers are the same as the coefficients, but not always. In fact, not even usually. The powers in a rate law are generally determined experimentally, and we define the overall reaction order as the sum of the exponents. We talk about reaction kinetics as being zero order, first order, second order, etc. If we know the rate law for a reaction, then we can determine the overall order of the reaction or the order for each reacting species. So now let's practice reading and using reaction orders in a rate law. Be sure to get into the habit of reading the question carefully and possibly even circling important clues. Pause the video here and work the problem in your notebook. And here is the solution. Notice that the first problem told us the reaction is second order. We did not get the order from the stoichiometry. We had to be told the order in the question. So we select choice B because this is the rate law where the sum of the exponents is equal to 2. In problem 2, we are given the rate law. Notice that the language of the answer choices is specific to the overall reaction and to the order with respect to each reactant individually. In this case, all statements are true.